Welcome to the Physics and Astronomy Colloquia. We're honored to have Barry Barish today as our speaker. Barry graduated from Berkeley. I think he went to Berkeley, it's the only school he went to. And then he went to CALTECH, and that's the only place he went to afterwards. So he stays in places for a long time. And he currently, for this, that shows you need a lot of stick with things for a long time. So I couldn't possibly go through his, everything he's been involved with. But clearly LIGO was a big piece of his career, starting 22 years ago. He was a PI when they got it funded, and then a director when it became a lab, and ushered through the LIGO 2, Advanced LIGO project. He's a member of the National Academy of Sciences and was a member of the National Science Board. And then so when Vivek is organizing this, so he comes to me after he invited Barry, and he said, "Oh, are you related to Barry Barish?" So yes, it's my dad. So I'm also thrilled to have him because it's very hard to see since he's traveling all over the place and doing various things. So welcome.
Do I have a pointer, advanced, or do I have to do it from here?
I don't have anything.
Anyway, I could tell you stories about him, but instead this is the only quote. There's a lot of quotes from Einstein, but this is the only quote about gravity. And it's wrong. I think he'd admit it's wrong, because unless you just talk about romantic love, or not love, because you can't help but fall in love with what we saw, which is this signal, whether you're somebody who waited 22 years, or you just read about it. It's a phenomenal thing to talk about. I'm going to kind of deconstruct this. This is the picture that was on the New York Times, or our Physrev letters, or wherever you first saw this. It's two traces, like you see in a lab. Time going this way, amplitude that way. The time scale is about 1/4 of a second. And it's two detectors, which I'm going to describe for you, about 3,000 kilometers apart in the U.S. One in the state of Louisiana, and one in Hanford, Washington. I'll explain to you why we use two, but for the purpose of beginning, it gives you a lot of confidence to see the fact that we saw this crazy wiggling signal at almost exactly the same time in two detectors around the world where we never see anything otherwise. This signal that you see is a wiggling signal that keeps getting narrower, which means higher frequency, and bigger. That's called a chirp signal. And it comes from the fact, as I'm going to describe to you, that objects that are merging, that come together, have higher and higher frequency and a stronger and stronger signal. They finally merge and then ring down. And this is the picture. There's a little line that you can kind of see through this. Well, let's see, the bottom one here takes the signal seen here, the signal seen here, and shifts it by 7 milliseconds. So keep in mind, these signals look exactly identical as long as we shift one by 7 milliseconds. And I'll explain to you why. You might be able to see a little line through here if your eyes are good. And that line, I'll talk about it in a different plot where you can see it better, is basically the calculations of what you should see in what I'll describe as what we've interpreted this signal to be. That's a black hole merger using Einstein's equations of general relativity. So this is the thing that we've seen, and I'm going to spend my time reconstructing it. So the first thing is that this is a picture drawn by a group that we work with. They're not a LIGO group, a group that does numerical relativity. And this is two black holes near each other. And we're going to see in the movie made from, and this picture is made from, not a computer animation, but a rendition on a screen of the calculations of the in-spiral that we observed. So this comes from a calculation. And just to give you a sense and remind you what these black holes are, let's look at this picture, which is a map here. Here's Riverside. If we go out to roughly Catalina, and we go the other way to the other side of Palm Springs, we have two objects, each of them small compared to this size, maybe 50 to 70 kilometers across. One of them weighing 29 times the mass of the Sun, the other one weighing 36 times the mass of the Sun, and they're going around each other at about half the speed of light. So that's physically what you're seeing. This is the computer rendition from the data that we saw. Now when they're going around, they're attracting each other and accelerating and radiating gravitational radiation, which we'll talk about. And finally, when they merge together, they make one object, but they have to dissipate all the motion. And so at the very end, you'll see a little ringing as well, and that's part of the signal. And if we went back to the very first signal, so that's that ringing that you can see. If we go back again to the first signal that I showed, I'm sorry, that what we've seen is this part where they're coming together. I'm going to talk about this part, which is the merger, and finally a ring down at the end. Those are the three features that we're going to describe and that we use to tell what's happening. So what happens? So they combine together, and then they're radiating energy as due to the acceleration, and the acceleration comes out, travels through space, and this event that we've seen happened 500 megaparsecs away, or 1.3 billion light years ago. It then comes to the Earth. I'm going to show you why, but it distorts space-time around the Earth by general relativity, and the gravitational waves change and distort the space around them. And we measure that not on the whole Earth, but in a detector called an interferometer. This is the picture of the one in the state of Washington, and I'm going to describe to you a little bit about what that is. Okay, so it comes to the Earth. Then from our data, we know that it came up from the southern hemisphere. We're not very good yet at telling exactly where, but to 600 square degrees, we know it came up here, and we live up in here somewhere. So just by comparing the signals in detail in these two sites, we can tell that what came first to Livingston, Louisiana. 7 milliseconds later, it arrived in Hanford. So that tells you something about where it was. And then because the antenna patterns of the two interferometers aren't spherical, but have a certain shape, by comparing the signals in the two, we're able to tell a little more, and we're down here. If we had a third interferometer, it could do true triangulation, and we do in principle have one to compare with, but they weren't running yet in Italy. We could get this down to about 20 square degrees, and in the future, by adding an interferometer that we're building in India, we'll be able to do it to a couple square degrees. That means that signals that we see, other signals that we see in gravitational waves, we can ask astronomers to look and see what similar signals they might have seen. For merging black holes, we don't expect to see anything from electromagnetic radiation, but if we see, I don't know, gamma ray bursts, the collapse of a star, many other things, we can compare the dynamics using different signals. So that's a goal for the future. So 20 milliseconds after it went through the southern hemisphere, it arrived in Livingston, Louisiana. That was this signal. 7 milliseconds later in Hanford, Washington. And then we have the fit from general relativity, which I drew through this. So now that's the history of the physical thing. Now let me trace kind of the history of scientists to get to the stage where we can understand this. So I'm going to start with Newton. We all learned about Newton in grammar school or high school or somewhere. And we learned that, and he wrote down his theory of gravity in his most famous manuscript, the Principia, which was published in 1687. And in that, he recognized that the problem of an apple falling out of a tree, a famous story, and that the moon goes around the Earth or the Earth around the sun, all should fit the same formula, the same phenomenology, and that was that it depended on the inverse square law. And he demonstrated that the inverse square law would make closed orbits for planets going around each other or around the sun. And he phenomenologically said it was proportional to the product of these two masses. And that the distance here, by doing the calculus, which he did, could be taken as the center of gravity. So you didn't have to integrate over anything. You just take it as the center of gravity of the two. And this was the formula. G was the constant. It took 100 years more for Chadwick to make a torsion pendulum that measured the big G, and his measurement of big G was essentially the same measurement with a lot more accuracy that we have today. So this was maybe the biggest thing that a physicist ever did, was have a theory of gravity, and it worked for everything for more than 200 years. And he called it a universal gravity because, as I said, it worked for the apple and it worked for the planets going around the sun. Okay. Then what happened? The next person in this story is a French mathematician, Urbain Le Verrier, and he is the father of what we call celestial mechanics. So he was a mathematician that did the mathematics for planets going around whatever orbits they have. And the famous thing that he did that made him basically the person that's identified the strongest with celestial mechanics is that he predicted the existence and the position of Neptune. And he did that by looking at the orbit of Uranus and applying the laws of Kepler and Newton and seeing that it deviated from that. And to fix it, he added another planet, which was Neptune. And he was dramatic enough to make this himself well known by doing this, because what he did is then decide to announce it, not like we would by going to a physics meeting and talking to our colleagues. He actually sent a letter to an astronomer in Germany from France, gave it 5 days to get there, and predicted where Neptune would be on that day. I told him to look for the planet, and within a degree he found Neptune, and that's the history of kind of Neptune being found. This gave him a lot of credibility, and that mattered for the next thing that he did, because in the 1850s, he then discovered a problem with the orbit of Mercury. Mercury is our closest planet to the sun, and he just described that Mercury had also a problem. And of course, since he succeeded once, he thought he could succeed again. And let me say what the problem is. The problem with Mercury is that it has a very elliptical orbit around the sun. There's all the planets around the sun. As it comes around, it moves a little bit each orbit, makes a daisy-like pattern. And you can calculate what it should be from Newton's theory of gravity and the positions of all the planets and objects. And if you do that, you get a number of 532 arc seconds per century is how much it moves. And if you actually look at the observations, it's about 10% more than that. So there was a discrepancy, which again, he decided meant that there must be an object between Mercury and the sun. He gave that object a name, Vulcan, which you may have heard that name. And people looked for it and thought they found it actually in the late 1800s, but they didn't. And each time it was thought to be found, it was disproven. At the time then, I'm just trying to set the scene, at the time that Einstein developed his theory of gravity, this was the only outstanding problem that existed. And it still had an unsolved problem that it could have been due to a planet or other bodies that were between Mercury and the sun. Advanced missions of NASA looked for it much after Einstein. So this continued. It's basically proven that there's no object larger than 10 kilometers now between Mercury and the sun by that satellite experiment. And so the only remaining history of Vulcan is Star Trek, where it was reinvented for a different reason. Okay, so Einstein, after developing the theory of special relativity in 1905, spent about 10 years. Why? And probably not because of the problem I just described, because it could have been solved otherwise. By some object, he couldn't have really felt he had to dedicate 10 years. So he did it for reasons of a genius, using a pencil and paper and feeling that he knew how to calculate gravity, starting from putting in accelerations, adding accelerations to special relativity. He had a lot of trouble with the mathematics, he had a lot of trouble developing it, but by 1915, he developed the theory of general relativity. And in that theory, the easiest thing to say is that it unifies space and time into a four-dimensional space-time. And that's a single word in terms of thinking about general relativity, but if I put it into Microsoft Word, I get a little wavy line underneath, so they don't understand yet that it's a single word. Anyway, so that's general relativity. Within a year, by 1916, which is then exactly 100 years ago, he recognized, Einstein recognized, general relativity wasn't really completely written down in all its rigor at that point, but he recognized similarities in the form of the equations that he had for general relativity and those in electrodynamics. And using that analogy that the two had similarities, he developed his prediction and wrote a paper on I'm going to skip this, that gravitational waves should be emitted. Before I come to that, let me say two things about general relativity. First is that when he developed general relativity in 1915, of course it got the right answer for Mercury going around the sun. We have a theory of gravity that has succeeded for more than 200 years. You don't replace a theory just because a new theory that's totally radically different solves one problem. It has to predict something new that matters. And that new thing, and the thing that made general relativity be taken seriously, even by the public, was the bending of light. So he predicted a second phenomenon other than solving the Mercury problem in 1915, and that was that light, when it bends, he could calculate how much it bends by general relativity, and he proposed that it could be observed by watching an object go behind the sun in a total eclipse, and watch as it goes behind the bending of light, and predicted how much it would be. And that experiment was done in 1919 by Arthur Eddington, who became Sir Arthur Eddington as a result. And the bending of light, and predicting the bending of light, and observing a bending of light is what made Einstein a household name. It hit newspapers all over the world. For physicists, of course, what he did in 1905 was fantastic. But for the world, it was the bending of light that made him capture and become a worldwide name. General relativity is something that was totally abstract and unused, and most physicists for many years didn't believe in it, or didn't use it, or didn't understand it. But we use it in absolutely everyday life. And so I want to point this out because it's another example of the fact that when we do fundamental physics, it can affect things in ways that we don't even know, even if it's as abstract and rigorous as general relativity. So without general relativity, GPS wouldn't work. We use GPS every day to keep us on the road. So let me explain that to you. So this is general relativity. So first, special relativity, which most of you know that when something goes very fast, and satellites up here, satellites, GPS works because there's about a half a dozen satellites that you can see at any given time. Some fraction of those you see, they're going at about 2,400 miles per hour each. And we all learn, when we learn special relativity, that moving clocks tick more slowly. If you take this speed, 24,000 miles per hour, the correction due to special relativity in doing the timing to tell where you are down here is about 7 microseconds per day. tick more slowly. But there's also a correction due to general relativity, and that's actually bigger, and the opposite sign. The correction due to general relativity is simply the fact that the satellites are further from the Earth, and the gravity that they feel compared on the Earth is only about a quarter of the gravitational field that we feel on the Earth. And so clocks by general relativity click faster at 45 microseconds per day. So let me put those numbers in perspective. The correction then for GPS, which is done on the satellites actually, is 38 microseconds per day. And how does that translate to staying on the road? The accuracy required is about 30 nanoseconds if you want 10 meter resolution. So if I go 38 microseconds per day, I move 30 nanoseconds in a couple minutes, which means that I wouldn't be able to stay on the road after a couple minutes if I didn't make the general relativistic correction. So as physicists, we should feel pretty proud of the fact that our most abstract theories, like general relativity, play a role in everyday life. Okay, so as I said, a year after he came out with the theory of general relativity, he predicted gravitational waves. This is the original paper, written in German at that time. And he did this from the analogy to electrodynamics, as I said. So the first publication was 1916. It had errors in it. It had errors of concept, and it also had a factor of 2 error in strength of the gravitational wave signal. So in our paper that many of you have seen, we simply say that Einstein predicted gravitational waves in 1916, and we discovered them 100 years later. The road's been a little rockier than that. First, he made a mistake of a factor of 2, which was corrected in the paper 2 years later. That paper also contains in it the formula you need, or the source you need to make gravitational waves. That is, he showed that they come from the quadruple formula. You know, all know electromagnetic waves come from an oscillating dipole. In this case, it's a quadruple. And that's gravitational waves. He also went through a period in the 1930s where he decided that gravitational waves maybe don't exist. He was trying to write the formalism more analytically, and in doing that he found singularities. He was working with Rosen, the same Rosen he worked with on other things, and they found a singularity and decided that gravitational waves were maybe an artifact. He wrote a paper called Do Gravitational Waves Exist? Submitted it in 1936 to Physical Review. Luckily for him, that paper went out for peer review. This is when peer review was just starting. He probably never had experienced peer review before. And the person that refereed it found a mistake in it, which had to do with coordinate systems, and told the editors of Physical Review, who told Einstein. Einstein said, "Go to hell." Literally. Said he would never publish again in Physical Review, which he never did. And he sent the paper, fixing it, by the way, a journal that is run by the Franklin Institute in Philadelphia. That journal is now defunct, but that article is just an analytical article making more steps toward what gravitational waves look like. This is what they do. So if a gravitational wave were to go through the board, like here, it distorts space-time in a way alternately where in one dimension it squashes, if these were free masses, just free to be moved by gravitational waves. It distorts them in this direction, squeezes it while it pulls it in the other direction. And you might think of it as what happens if you go to an amusement park and you go into one mirror and it makes you short and fat, and the next mirror makes you tall and thin, and you go back and forth. And that's what happens. Do you have a question?
Yeah, what does it do to the clock?
What is what?
The gravitational waves?
I'm sorry.
Do they do anything to the time dimension?
No. No. The question was whether gravitational waves affect time, like I was talking about before, and the answer is no. Quickly, we can talk later. But what it does is change space, distort space in a way that we're going to detect. The time is the time evolution of the gravitational wave signal, which I'll also talk about. Anyway, So if we want to detect something like this, then we're going to detect somehow that we got shorter in this arm while we got longer in that arm. And that's a match to the technique that we use, which is called interferometry. So the idea is that in interferometry, you send a laser beam and you divide it in two. You send it down this arm and this arm. And as long as these aren't moving at all, it takes the same length of time to go this way as this way, and the light, when it comes back, you set it so it cancels each other, and the sensor detects nothing. It's dark. If one of the arms moves relative to the other, then the time it takes for light to go down one arm is different than the other arm, and some light comes down into the sensor. And in a simple-minded way, that's how an interferometer works. But it's the most sensitive instrument we have on Earth to measure the difference between two distances. So it's very hard to measure accurately the length of a meter stick. But to measure the difference between two things, if we're good enough, we can do it phenomenally accurately, which is what I'm going to show you. First, let me talk first about the strength of the signal. And let me do that now. So the first thing you might think, if you're going to measure gravitational waves, is after this theoretical history. It was about the 1950s when theorists agreed there should be gravitational waves. There was a famous meeting in North Carolina, kind of where the famous physicists of the day got together. And after that meeting, I think everybody agreed theoretically that gravitational waves exist and what their features would be. So at that point, it became an experimental problem, but we didn't know how to solve it experimentally. First thing you'd ask is, why can't you do it like Hertz did for electromagnetism? What Hertz did is take in one lab, take a dipole source, vibrate it, and measure in the next room the emitted electromagnetic wave, and then he took his detector and moved it back and forth to show that it was wavelength. And that was in the 1880s. So why couldn't we do the same thing for gravitational waves? And certainly you want to. As an experimental physicist, the thing you'd like to do is control all the variables when you do an experiment. You don't like to be in a place where you have a lot of unknown things. So I've spent a lot of time doing neutrino physics, and one problem with neutrinos is you don't see them coming, you don't know a lot about what they are, and that's a handicap. So you'd like to create something like a Hertz experiment. So I'll do it in a Gedanken way so you can see that it's not easy. So I've imagined a nice modern laboratory and something that can make a quadruple moment. That's a barbell that spins around. So I've put super heavy weights on the ends, 1,000 kilograms, separated by, say, a meter, and rotated at 1,000 times a second, get out of the room, and go away 300 meters. You have to go a lot further than 300 meters to see the wavelight, but I'm trying to make this as big as I can. So I've exaggerated all the numbers as much as I can, and I calculate the strength, and then I will rotate it. I calculate the strength in the terms that I'm going to use. I'm not going to go through the formulas for you today, but it's the same terms that I'm going to use. This is the so-called strain and general relativity. The amplitude of the signal is 10 to the minus 35. The signal that we saw is shown here, the one I showed you at the beginning, two black holes going around each other, and the parameters are here. They're each 30 solar masses. Their radius is about 100 kilometers. They're going at 100 times a second, as I showed you in the plot, and they're 500 megaparsecs away. If I do the same calculation with these parameters instead of the barbell, I get an H of 10 to the minus 21. So doing this experiment in the lab, we're 14 orders of magnitude away from it being possible. So it's not possible. You don't have to look at this part, that's just the calculation, but look over here. This little h is what's called the strain in Einstein's equations, and it's related directly to a change of length over length, which is what we measure in an interferometer. We measure that one arm got longer or shorter. You can put in the factor of 2, but it's a delta length over length, which is proportional to the strain, and the amplitude that we're going to try to do is 10 to the minus 21. We don't know how to do the one in the lab. The byproduct is we don't control everything because we go in space, but then we find a very interesting phenomenon that's our source. So that's the byproduct. Okay, so what do we expect to happen? So this is just a freehand drawing of what we expect to happen. We have a first phase, it's an in-spiral. These objects themselves are spinning in some way. They're in-spiraling around each other and accelerating at the time, so they're emitting gravitational radiation. That's the part that was mostly what you saw in that graph. Basically getting bigger and narrower, meaning higher frequency, basically then they merge. And when they merge, we don't know what that looks like. That's merging into a black hole. It's the strongest field of gravity that we know. And I'm going to come back to the fact that that's maybe our future, is understanding how that all works. And at the end, it rings down with some frequency. Depending on its masses of the objects, the features will be somewhat different, how long they'll go, and I'll show you that in the data that I have. So how do we look for them? This is the scheme. So we have an idea that if the kind of objects we'll look for, if we look for binary objects, which is what I'm going to concentrate on today, there's other objects that are sources of gravitational waves, but I'll stick with the binary objects. Then there's a plane of sensitivity where this goes from 1 solar mass objects up to maybe 100 solar mass objects. And we cover that whole space somehow in searching for signals that are inside of a lot of noise that is kind of the limiting sensitivity of the interferometer. We can see below this noise level, which is random, by taking shapes that we calculate and know and are looking for, and multiply it by this shape. If we multiply it by the shape, then, oops, I just screwed up my movement. So if we multiply it, we don't see anything, and then we get to something that we're looking for out here. We can build up a signal because it looks like we see the real shape embedded, and we see a signal, and then we look further. So this is called using a matched template scheme. We use actually 250,000 templates to compare with every piece of data that we have, and those templates are calculated using numerical relativity, something that we can do today and couldn't do years ago. So let's talk about the experiment. So that's how we look. Now I'm going to build an experiment to do it. The first attempt, after the 1950s, when theorists agreed that such a phenomenon as gravitational waves do exist, the challenge is experimental, was taken by Joseph Weber. He was an experimental physicist, very much an instrumentalist, who had been in the Navy. Then he went to Princeton and he heard about gravitational waves from Dickey and Wheeler, and he decided he knew how to attack the problem and detect them. And his scheme was to make a big bar of aluminum. And the big bar of aluminum, if you go up and you hit it with a hammer or something, will ring at some resonant frequency depending on its geometry. And the idea then that he had is to instrument it with some very sensitive instruments that could see the distortion of the bar when it resonated at those frequencies due to a gravitational wave. Very clever idea. And he began looking for these effects in resonant bars in the 1960s, using PZTs around the midline, as you see there, to absorb the signal and find the signal. It was a very clever idea. He basically then announced in 1969 that he had detected gravitational waves. This is the figure from PhysRev letters in 1969, where he attributed this peak, which was done at Argonne Lab near Chicago, and secondly at the University of Maryland, as due to a gravitational wave signal. This turned out to be just an artifact, but unfortunately he repeated this 2 other times in his career, claiming he had detected gravitational waves. And so the person who was really the father of this field, an incredibly clever experimentalist, wasn't a very good scientist and spoiled his career in my mind. But he has a legacy in what we do in 3 places that are really important, and I'll give him credit for it. First, the sensitivity calculations that we do, and I'll show you, which tell us where we run, how sensitive the instrument can be, and what limits it, is exactly what he did. We have different kinds of backgrounds and so forth, but basically we follow the same recipe that he did. The second thing is that, and he did it here, that we do a coincidence, and you saw we do it, between two detectors that are widely separated to give us confidence that we see a signal. And the third is, I'm going to show you in a little while, is how do we determine how significant a signal is. And he used a scheme, which I'll show you, called time slices, and that's just what we do. So we inherited a lot from him. Not only did he start the field experimentally, but he basically used some ideas that are the same ones we've incorporated from him.
How sensitive was his instrument?
Now his instrument is 10 to the 6 times less sensitive than the detections that we've made. Part of that, a big part of that, is the fact that our detectors are 4,000 meters long. His are 1 meter long, so that gives you more than 3 orders of magnitude. Just the effect, delta L over L. The rest of it is just the fact that we've made a much more sensitive device to see small effects with an interferometer than you could ever make with a standing device like this. They improved over him by about a factor of 10 by going to low temperatures after he stopped the field. But once LIGO came on, people using bars either joined us or quit. Next, in the 1990s, Hulse and Taylor were using the Arecibo radio telescope to look at pulsars in our galaxy. And they were studying a pulsar that goes around 17 times a second. They were studying it long term to measure all its parameters. And what they noticed is that it was modulated by something like an 8-hour period. And that was then quickly interpreted that this was a binary system, not a single spinning pulsar. So they had found a binary system where one object was spinning at 17 times a second, the second one going around the first one once every 8 hours. And they measured as much as carefully as they could all the parameters of this system over a period of about 20 years. And what they measured is what I'll show is what you expect from general relativity, and that is as you go around each other here, you accelerate and therefore radiate away gravitational radiation. And on each turn then, it loses a little bit of energy and inspirals. And as it inspirals, the frequency or the period gets a little shorter and shorter and shorter and shorter, and eventually they merge. We're seeing the very last pieces of this kind of merger, not for neutron stars, but for black holes. And if you took the system that they're looking at and we wanted to detect it, we'd have to wait about 1 million years, which is longer than the patience of a graduate student. So anyway, what they did instead is a very careful measurement of this 8-hour period. And this is the difference, or how much it's speeded up in seconds over a period of about 20 years. It's speeded up about 20 seconds or 25 seconds in 20 years, from 1975 to the year 2000. And the dots on here are the data, and the line is the line that you calculate using general relativity, using the parameters that they have for the system, the ellipticity, the masses, and so forth, that they have for the system. What to appreciate, and why this is so fantastic, is that this is not a fit. So usually we see a line like this and it's a fit to the data. This is strictly a calculation from the parameters of that binary system laid on top of the data. So you can see how good it is. They then won the Nobel Prize in 1993 for this indirect evidence, if you want, because of the radiation, for gravitational radiation. Okay. This is just a quick movie so you can see physically what LIGO looks like, and then I'll show you the insides of it a little bit. So now we're going to change to interferometers. Our interferometer is 4 kilometers long. This is in Livingston, Louisiana, where there's a lot of trees and water and so forth. This is some of the optics. There's very, very precision optics. Our control room, and the two of them are identical. They're 3,000 kilometers apart, very different geology, but identical instruments. And when we change something here, as we learn to control things in a better way, get rid of some noise or something, we immediately port it to here or vice versa. So we keep these instruments almost identical, And you'll see how successfully we do that when I show you how the sensitivity curves of the two, even though they're very precision instruments, very different geological place, they look identical almost. So let's see what actually in practice limits you in how well you can do this interferometry. Remember, we want to measure delta L over L to 1 part in 10 to the minus 21. That was our goal, in order to see the signal from that, and that was what we were able to do. So we have this simple interferometer picture, a laser, a beam splitter going both directions, and a photodiode, and we make it so that this one, when it comes back, interferes such that they cancel each other and no light goes to the photodiode. So the first thing that limits you is that we have 4 kilometers long, and the photons that go from here to here can scatter on gas. It might lengthen the path that it has when it comes back, and so then now it's out of phase. So we have to work in vacuum, and in fact the vacuum has to be quite good. It's up. And so the vacuum system that we built, the pipes that we have in those pictures are 1.2 meter diameter, made out of stainless steel, 1 millimeter stainless steel. And we have 16 kilometers of it, all at high vacuum. It's the largest high vacuum system by far in the world.
Why would you use such a large diameter?
We have a large diameter because our whole laboratory is inside this vacuum. Therefore, we can do many things. We can run test beams down it that don't interfere with the main beam. We can have several interferometers, for example, in the future, one that runs that looks at narrow band frequencies, one that's wide band, and so forth. So that's our laboratory, so we made it good. It's a good question. So the second thing that limits you is the laser itself. I'll show you a picture of our laser, but it's not like the one I have in my hand. It's probably the most stable laser in the world. It has to be a single line. We want the line to be one frequency. I'll show you why in a minute. We stabilize it by locking it into cavities in wavelength, in its amplitude, and its pointing. And that's a quite complicated system. We work in the infrared. These are neodymium YAG laser at 1064 nanometers, and it's the most powerful one in the world. The first ones we made were commercial. We wanted to make them with industry so that we could rely on them, not like we didn't want to have to go in and fix our lasers all the time, so we didn't have our graduate students build it. We made it in industry. They put it on the market. I don't know if they ever sold any, except to us. The next thing that limits you, I have up here, is the test mass itself. It has to be stable. But no matter what we do, these test masses can be shaken by the shaking of the earth, by anything that disturbs them. We can't put them like you do in freshman or sophomore laboratory, whichever you do here, where you have to first look at an interferometer. That is, take a stable table and bolt these things down because they have to be free masses to move from the gravitational radiation. So we instead hang the masses from wires. These are very special wires. They're then pendulum that move back and forth, but we have to control the movement of the pendulum. The pendulum frequency is much lower than the frequency we're looking for gravitational waves. We make a pendulum that swings at once or twice a second. We're working at hundreds of times a second. So we just have to control it enough to so-called lock on a fringe. So we have to isolate ourselves from seismic effects. I'll show you a picture of how we do that. And that has been the key to this measurement that we made, this discovery we made. The third thing is that we have test masses, but test masses are made out of molecules and protons and neutrons, and they move around at room temperature. So thermal noise, KT noise, is another thing that we contend with. We deal with the idea, play with the idea, and the Japanese are trying yet of cooling the test masses, but you have to cool them without shaking them. That's very difficult. Lastly, we get to noise. If we can lick all those, we get to noise problems that are basically quantum mechanical. That is, if we keep increasing the power of the laser, or the number of photons, that helps us make the measurements very well at high frequencies. But if we do that, it puts radiation pressure and moves the mirrors. So we have a back and forth between how to do that. There's ways around it, which are called squeeze light, for example. So what we end up with is a curve that looks like this. What we have available to us is this shaded area to do our experiment. We're limited at low frequencies by seismic noise, so notice it drops very, very quickly. That's the shaking of the Earth. It falls its frequency to the 4th power, and below 10 hertz or so, everything cuts off. That's why our ears have, by evolution, cut off at low frequency. The Earth is just much too noisy at very low frequency. So we work in the same band where the Earth is quiet. We're not doing any audio signals, but basically at low frequency, we're cut off by the seismic shaking. At high frequencies, we're cut off by how quickly you can sample the signal, just like your ears. In our case, we sample the signal by how many photons we have. That's called shot noise for interferometer experts. It's called photostatistics for, say, a particle physicist. And in between, we're limited by what I call thermal noise, KT noise. So as an experimentalist, we have the awful problem that we don't have one background we're trying to deal with, but 3 different ones. And if we get better, we have new ones to deal with. So that's the game. You'll notice the level here is something like 10 to the minus 22, so we can make measurements at 10 to the minus 21 for the sun signal. The next graph is the actual performance of the interferometer we have. Ignore all the stuff underneath. It's our ability to understand what created all the backgrounds that we measure. But it looks like the one I showed you. This is the low frequencies, seismic. This is limited by thermal noise, and the high frequencies by basically how many photons you have in your laser. You'll also notice all these spikes. They cover about 1% of the frequency range, and they're due to all the natural resonances that exist in any experiment, but certainly in our experiment. There's resonant frequencies for the wires, for the stands, for the electricity, which is 60 hertz, and so forth and so on. So there's many, many frequencies. Many of them we try to get rid of. They're stable, but we notch them out. So about 1%, we just know what they are, we notch it out. It looks funny on this graph, you leave it there, but that's the problem. So we built the interferometer. It worked this well. You can't read the scale very well, but this is about 10 to the minus 21. And we ran from 2005 to 2010, at which time we had developed all the techniques to make this better. And we set a lot of limits on things, but we didn't see anything. Then we turned ourselves off. We got funded. We turned ourselves off to build Advanced LIGO. Advanced LIGO, this is showing the final sensitivity that we calculated and the final sensitivity that we observed here in initial LIGO. This is already putting in a higher power laser, so it came down here for the very last data run that we took. But we took what was in initial LIGO and made a goal to increase everything by a factor of 10 over the whole frequency range. Now let me point out that a factor of 10 for us is a huge factor because we're measuring an amplitude, not a power. And so if our sensitivity is improved by a factor of 10, it means we look a factor of 10 further out in the universe, and the volume of galaxies and stars or black holes is 1,000 times, 10 cubed times greater. So any improvement of the sensitivity that's significant at all, a factor of 2, gives us a factor of 8 more sensitivity. In contrast to, say, more data at CERN, where you gain as a square root of 2 in statistics. So we have a big effort to try to improve down to where we're fundamentally limited. And knowing that we haven't developed the technologies and the money, we set a goal of a factor of 10. And that's Advanced LIGO. At high frequencies, the primary way you make the gain is just increase the number of photons. So we have increased from a 20-watt laser to a 200-watt laser. And that's been installed, and we'll talk about it. At medium frequencies, in order to lower the thermal noise, the KT noise, we have a much fancier system, suspension system. I'll show you a picture of that. And heavier and better optics for the reflecting of the light. And at the low frequencies, and this is probably the key thing that enabled us to make this measurement is we've improved the seismic isolation, and I'll give you a quick reason how. This is a picture of our optics. They're great big pieces of fused silica, polished to the same accuracy as the best telescopes. They have a coating on them, a 20-layer dielectric coating that reflects the light at 1064 nanometers, the wavelength of our laser, and they weigh 40 kilograms. And so they're shown here in the interferometer, but that's the test masses. They're hung then from wires. Originally, we used piano wire in the initial version of LIGO, and initially we kept this swinging thing in steady by having actuators and magnets on the test mass itself, which stabilized it. And we've improved that for Advanced LIGO by making a multiple pendulum instead of a single pendulum. And the bottom piece, which is the test mass we want to use, or the mirror we want to use to see if it moves, has nothing on it. It's just hanging. And we control it by moving around the upper stages. It's tricky to do that, but we've learned how to do it. This is again a picture of this test mass, our mirror, which to the eye is perfectly clear, beautiful glass. But we look at a different wavelength. Now the seismic isolation, which is the big improvement for us. Originally we used shock absorbers only, which 4 layers. You can see the layers here, which were basically damped springs like you have in your car, only 4 layers of them, all passive. And that system got us to where we were for initial LIGO. But now what we've added, so those are shown here, this is the multiple pendulum, this is the springs, the layers for the springs, but now we've added a very fancy system of active seismic feedback. Think of the earphones you use on an airplane, and they measure the ambient noise and then cancel it. It's the same idea, only in our case, it has to be 6-dimensional. We have to do the 3 linear dimensions and the rotational dimensions, so it's a 6-dimensional correction for ambient shaking. It survives at each stage the passive seismic isolation, and that system then to work right has to be done so that when you fix what you think is noise in one direction, it doesn't affect the signals in the other directions. You don't know how to do that ahead, even if you design it on a table accurately, because looking in situ, looking down, we see sand or water or concrete. Looking up, we see air, and so the environment is different. And so we need a big program to effectively diagonalize the matrix so that when you make a correction for one direction of the 6, it doesn't affect the others. That takes a lot of work. We haven't done all that yet. But that's part of the improvements in the future. This is our real laser. You can see how complicated it is, which is 200-watt neodymium YAG laser, very well stabilized. Okay, so then we put it all in. We built it between 2010 and 2013 or 14, and then we started installing it. And this was the same curve that I showed you that we used for 5 years or so for initial LIGO. And this is the improvement we found. This is the improvement we've designed to. When we got here, because of the fact that we gain is the cube, we decided to not keep testing to get down here right away, but take our data. So we had a factor of 3 improvement everywhere, but at low frequencies, the improvement is actually a factor of 100. So a factor of 100 improvement in sensitivity is a factor of 100 cubed. I'm sorry, 100 in this sensitivity is a factor of 100 cubed in the volume or the rate that you have for gravitational radiation. And it's why we couldn't see the same kind of signal in our previous 5 years of running that we saw, and I showed you on our first slide. So now let me show you a little bit about what we saw and what it means. Okay, so this is the 2 signals, same as I showed you on the very, very first slide, only now we know that this is the in-spiral, this is the merger, and this is the ring down. This is the best fit to that signal using general relativity to calculate the binary systems. I'll show you the parameters that we fit to this data. And you can see that it looks like this. But to see it even better, we subtract one from the other, and I plot here the residuals. And you see no, it wiggles back and forth, but there's no sign that it's misdescribing the whole shape. The bottom one is the so-called chirp signal. That's just the frequency. As the frequency increases, it gets brighter, and so the amplitude increases. Next, I want to show you how we know the significance of this signal. So this is the number of events of any type we saw as a function of how strong or good the signal was, making a coincidence between Livingston, Louisiana, and Hanford, Washington within plus or minus 10 milliseconds, and it drops off to one event, 10 to the 0. One event here, one event here, and this is the event I showed you. So it has this, on some scale that we use, which I won't show you the formula, it has a detector significance of 22. Then to test the background, these are in coincidence plus or minus 10 milliseconds at two sites. Then we look at off times, plus 20 milliseconds, 40 milliseconds, 60, and so forth, and trace out this whole curve for what significance we find. We don't see anything as big as this in a month's running, and this actually, I'll explain to you, is the real signal in one interferometer against just noise in the other one. Because if we say this is a real event then, and I remove it from the data, and just take all the bins and compare them with each other, I get this curve here. So this event stands out, way out, and the significance is shown up here, and it's greater than 5.1 sigma. The 5.1 sigma is just limited by how many bins we compare, off-time bins we compare, how long we did that. So that's the significance. This is again the signal, and I showed you this more or less. We start as an in spiral, they merge together, and they ring down. That's its signal. But look at the bottom, because I want to emphasize it. How far apart are they? That's over here. This is in a unit which we call the Schwarzschild radius. It's about 70 kilometers. So it starts maybe a few hundred kilometers apart. We saw that. And by the time they merge together, it's maybe 100 kilometers apart. This one is the velocity. And in the movie, you couldn't really feel that because we made it so much smaller. But they're going, even at the beginning, out here where we see them at about a third the speed of light. And by the time they merge, they're going at something like 6/10 the speed of light. So if you want to interpret this as anything other than black holes, you have to realize that all this mass is in less than 100 kilometer space, 50 kilometer or so space, and these objects are going at relativistic velocities. So by that being the only way, we assume that it fits so well that our interpretation is that it's black holes merging. We know from the equations how to pull out the parameters. I've only written down the first order one here for what's called the chirp mass. The chirp mass is this term here. These are the masses of the two merging objects and the final mass, and the frequencies and how much the frequency is changing and so forth. With that, there's another order which I haven't shown. We can measure the spins and so forth. We can determine essentially everything about this event from this if the data is good. And I'll show you how well we can do. So with this, we basically measure even if the precessions are misaligned, the sky location, the distance, the binary information on the two incoming ones, and this is just examples. This is the mass of one of the in-spiral ones versus the mass of the other, the probability curve, so they're both around 25 or 30 solar masses. This is actually the measurement. The total ends up being 62 for the merged mass, whether we do it by calculating it from the in-spiral or we do it from the final amplitude and spin, we get the same answer. 62 is 3 solar masses more than what we started with, so 3 solar masses of energy and about a quarter of a second dissipated. It was really, in terms of energy, the brightest object in the sky for a quarter of a second. Okay. So doing the numerical simulations of the black hole, we determined that the mass of the final object is 62 solar masses. And also it has a spin. And that spin can be, you started with spinning objects, that spin has a maximum spin that a final Schwarzschild black hole can have. These are finite, this is finite but not maximal. Maximal would be 1. So we get a spin of 0.7. As I show you more events, you'll see that that's true of the others. So these are the main parameters that we measure. Okay, that was the event announced February 11th. We had already finished our data run, which ended January 12th, and had observed 2 other possible events. One in October, which I'll call a candidate today, and one in December, which we knew about when we came out in February, but we weren't ready to come forward with it yet. Those are very different from each other, and I'm going to treat them like 3 events, although I'll represent this as a candidate. I'll show you why, but I want to show you how different they are. So this is the 3 events where amplitude is this way. The first one was the biggest signal, and you can see it's big compared to our noise curve. And it came in at low frequencies, got stronger when they merged and then dropped off. But it didn't stay in very long, so we only saw about 10 wiggles before it merged. The second event, which is the one seen and announced in June and seen on Boxing Day, December 26th, is the red one here. It came in, went to much higher frequencies, and then dropped off. We actually saw something like 200 inspirals, and it finally merged here, so looking in our apparatus, it went much further. The third one, which I call the candidate, is a little weaker, and it came in and died off here, and it's somewhere in between. The reason it's weaker is that it's further away, and I'll show you that, and not because anything about the characteristics. The second event, we didn't find with the naked eye like the first one. We found it with a match filter, as I described before, and this is the picture of kind of looking through the noise signal and seeing that we saw a spike by doing the product in the way that I showed you before in the 2 detectors and saw it in both detectors. So it stood out. It is very different in characteristic, as you've seen the first one, of all these oscillations. Having all these oscillations, we can take the different parts of it and analyze it in great detail and try to see differences from general relativity or the effects themselves. And this is again the velocity getting up to half the velocity of light. And this is the merger coming together. And you'll see characteristically it's very different from the first event. This is all 3 events shown on the same plot. So this is the spin going this way, maximal spin here, and they all have about 2/3 of the maximum spin. This is the 2 events. This is the event that is a candidate, so we don't give it the GW for gravitational wave signature, and it's just because it's further away, the signal's a little weaker. So it's about a megaparsec, 1,000 megaparsecs. Okay. We can also look and test general relativity, and the last thing I want to do is talk about the science then that we can do even with a couple of events. First thing is that we can calculate the final spin and the final mass in 2 different ways. One by just this in-spiral and using the formulas of general relativity, and the last, the actual amplitude of the signal and the final ring-down frequency. And we get these circles here that overlap, giving us this final answer. And they're completely consistent with each other. So in a qualitative way, every time we take a different part of this spectrum when we calculate general relativity, they're all consistent. There's no inconsistencies that we've seen. We can be a little more quantitative, and we've taken the whole thing and tried to ask if we take the, really for people that know general relativity, which comes in different terms, and you let any one term vary, can you vary it enough so that it can get, that it's significantly away from the mean value, and this is just all the terms, and they're all consistent. We don't see any difference from general relativity. In another sense, we can test general relativity by asking whether the data we have is consistent with graviton, which does not exist in general relativity, having a finite mass. So what would a finite mass of the gravitational wave do to the gravitational wave? It adds a dispersion term. And so the different frequencies travel at somewhat different velocities, and you get a slight distortion in the wave that we've done. So I can ask myself, with the wave I have, how much distortion can I allow within the accuracy that we measured? And it's pretty impressive. It's the best measurement that exists on how massive graviton could be. It's less than 1.2 10 to the minus 22 eV over c squared. Okay, that's general relativity, and I think in the long term, the science of understanding general relativity, not where we use GPS, but where it's the most interesting, and that is in the strong field limit, will be done with gravitational waves, where we can use black hole mergers and events like this to study the really strong field of gravity, but of course we need much more data. The second is new astrophysics done by looking with a different type of instrument, in this case gravitational radiation. So what have we learned in astrophysics? First, we've learned that definitively, because we detected them, that stellar binary black holes exist. That's good. We've also learned that they form in binary pairs within the lifetime of the universe. We've also learned that they not only form, but they merge within the lifetime of the universe. And lastly, and maybe most interestingly, we've learned that the masses can be very high. This is a puzzle, because at the beginning we of course looked as experimentalists for large masses, but it's expected that black holes had to be higher than 2.5 solar masses or so, and couldn't be much larger than maybe 10 solar masses, because the progenitor star that collapses to give the black hole couldn't hold together. So the general sense, and everything that was studied previously, was that black holes were less than 10 solar masses. Our first ones were 2 30-mass black holes making a 60 mass, and the last one ends up making a 30 solar mass black hole. So we now have to explain the large black holes. We don't have data to do that, of course. It could be because we can have larger stars that can be progenitors, in which case it means they have to be maybe in what people call low metallicity environment in the universe. Or maybe we have a lot of them and a lot of mergers that make them grow up into mergers. We don't know anything. We've just observed the first few events. So, inferring the rate we can do also, and we've done that. The rate, well, we can take different models, and we at least know the rate's not zero, and we have a rate in gigaparsecs per year using different models, so we can use that to predict what our future rate is on these black hole mergers. So that's where we are. We're starting to, that's all the data we have. I've shown you everything we have. We're starting to run with some improvements in the detector by, I hope, December 1. We're starting an engineering run soon. If that goes well, then we'll start December 1st. And that run will be longer than the first one, and we expect to see more black hole mergers, maybe some other sources that we're looking for, in particular binary neutron star systems. So the first source that we saw was black hole mergers. We want to look for black hole neutron star systems, neutron star systems, and of course pursue the black hole binary systems. Other things that we do is to look for burst signals. And examples of that are gamma ray bursts, the collapse of a stellar collapse of a star, to the extent that they have a quadruple moment when a star collapses. If it's got a quadruple moment and has some asymmetries, which we think it does, then it'll give a signal for gravitation. To really understand stellar collapse, you'd like to understand the collapse itself, which is gravitational waves, the nuclear part, which is neutrinos coming out, and the optical part, which is the shock wave that we see, to really understand what happens when a star collapses. A last source, maybe the most romantic, and something we can't do now, is that potentially gravitational waves are the best source we have to go back to the earliest times in the Big Bang. All our information comes from photons, but photons get absorbed. And so we can't see back to really, really early times. To see at earlier times, we have two other choices: neutrinos. The problem with neutrinos are that neutrinos made in the early universe are thermalized, and so they're very, very low energy. And low energy neutrinos have a very small cross section to detect them, and so you need detectors the size of the Earth living motor. So it's essentially impossible. The best source is gravitational waves. either seen directly, maybe not at our frequencies, but lower frequencies, or gravitational waves as they affect, for example, the cosmic microwave background. They make an imprint on the signals from the cosmic microwave background, polarization signals that can give us information back further than the cosmic microwave background signal itself. Lastly, we look for sources like spinning neutron stars. One second. Spinning neutron stars, and to the extent that the pulsar has any quadruple moment, we can detect it. And that is that we've looked at the best known pulsars already and shown that, for example, they don't have mountains bigger than a millimeter from the sensitivity that we have. But younger pulsars, when the frequencies are still changing and they result from, say, the collapse of a star, are prime targets for detecting the gravitational radiation. It's a very hard computing problem because we don't know where they are and where the frequencies are. So we're limited by our computing. There was a question somewhere. Yeah.
So from technology point of view, how many years you're behind to detect primordial gravitational waves?
We don't know how to do it at our frequency at all. It's probably more likely it can be done in space or with pulsar timing arrays. In our frequency, I would say we have to go not only several generations of detectors that we dream about, but we have to rely on some sort of very inflationary model that makes the amount at high frequencies large enough to detect. We're probably, if we don't use inflation at all, we're somewhere like 7 or 8 orders of magnitude away at the present time. So we might get a couple orders of magnitude from sensitivity, but the rest would have to come from some sort of inflationary model. Okay, I'm essentially done. I just want to point out the future use of these in correlation with electromagnetic signals. I said it in words before, but presently with 2 detectors we don't localize anything very well. But within the next decade from now, we'll have enough detectors to get resolution in space for whatever we see to a couple square degrees. And at that point, astronomers might frown. I don't know if there's one in the front row, but they can search within a couple of square degrees. Giving them 600 square degrees is not much help. So the future of this is very much, I think, like astronomy. Oh, it's over many decades, so it's not what's going to happen tomorrow. We've seen first what we've detected on the ground and maybe what the potential is on the ground. There's a rich future doing this in space. And it's like changing frequencies for astronomy. If we go into space, and the project's called LISA, then we, instead of look at 10 to 10,000 hertz as our band of frequencies we can check, we look from 10 to the minus 1 to 10 to the minus 4 hertz in an experiment which is funded in Europe and may get funded by NASA again, it was previously, to have 3 satellites in space widely separated that measure the time to go back and forth between this close triangle and measure these frequency bands. Then there's pulsar timing, which gets to even lower frequencies, and that people are actively pursuing. And lastly, as I said, the imprint on cosmic microwave background signals due to the polarization effects that would come from gravitational waves. So what we've seen, most of us that are in this field believe, is the birth of a new kind of astronomy. It's taken a long time to do this kind of astronomy. It's going to be a process of years or centuries, just like that, to do everything that can be done. But we've opened the window. So thank you.